Hi, my name is Miles Franklin, and my project was understanding the projected shifts in the U.S. job market as they are predicted by the Bureau of Labor Statistics. So the goal of this project is to first show a mini web scraping project where we actually go to the U.S. Bureau of Labor Statistics and extract the data. And then with the data that we have, we're going to create a model that predicts the predicted number of jobs for any available position. So that process is going to require us to explore different models and figure out, once we have our desired model, what's the best way to select the criteria or the hyperparameters for that model. So just taking a little closer look at what we were scraping. The Bureau of Labor Statistics has a website where it has all of the, I guess, reported jobs in a list format. And when you click on any one of these hyperlinks, it gives you to a summary or a quick fact summary of that position. So we see fields like median pay, so an hourly and yearly wage, the required education, how many jobs it has today, and the expected change coming between today and or 2019 and 2029. So our goal was to take this information from each individual hyperlink and create a nice, clean pandas data frame that has all of those rows as column information. So kind of as you can see on the top part of this slide, that's exactly what we were looking for. So all of these column headers are the uh, row titles that we were looking for from the previous slide, and we've converted them into columns, and then each row is that represents that position. So from there, the next step is to figure out what features we want to keep for the model, what features make sense, what features don't. And so something like URL, for example, was stored, but not in this image. But clearly, we don't need something like a URL in a prediction model. Nor do we really need the job title, since there's not really any information that the machine can grab looking at title to title. It would, however, be helpful if maybe we grouped these titles into categories, maybe saying something like a nurse manager, or nursery manager, or a preschool teacher all fell under like the umbrella of education, and we gave it a categorical title. But in the form that it's in right now, where it's just job title, just not super helpful. Um, However, when we look at columns like typical entry level education and on the job training, those are more categorical values. So there's only going to be so many entry level educations to choose from. So that's going to be a category that we can convert into numbers so that's a little bit easier for the models to understand. Similarly, for on the job training, and or actually, no, not job outlook. Yeah, similarly for on the job training, there's only so many different ways to spin that, if you will. Uh, so it's very easy to cast it as a categorical value so we can put it into numbers for the model. Um, and yes, moving along. And so now that we have information kind of in that format, we did a little bit of elementary analysis just to get an understanding of what the job market looks like, just to kind of report some summary statistics, if you will. We The image that we're looking at now is we grouped the data frame into chunks based off of required education level, and then we look to see, okay, organize this data frame based off of the who's expecting the hardest hit in employment change between 2019 and 2029. Um, and so as you move down from formal no formal education down towards doctorate, uh, predictably the higher education roles tend to stay or tend to not experience as great of a decline. Although I believe there was an interesting example concerning pharmacy as an industry. Uh, but if we look at something like cashiers, for example, like the very top row, we can see that they're expecting an enormous hit to their overall employment availability. And so this wasn't really fundamental to the prediction model, but it was just kind of helpful to have more of a summary statistic of what the data already says before we try to make any predictions based on that data. So further information for this would be available on like in the notebooks, where you can play around to see what if you want top 10, top 20, etc., how you want to organize those roles. So after we've done some summary statistics just to get a little bit more familiar with the data, the next goal is to figure out what model we wanted to create. So we first looked at a linear regression model, just because it made sense. We're looking to predict a number of jobs in 2029. And since a number of jobs would be a continuous value, we were expecting that maybe a regression of some sort with enough variable input would be able to capture the information. Unfortunately, a linear regression was far too simple of a model and wasn't able to handle much of any of the variability in the model. And again, that could very well be solved by adding categorical values and doing a little bit more feature engineering to figure out what trends were to help the model figure out what trends were in the data. So given that, we decided to switch over from linear regression to decision trees. And interestingly enough, like I said earlier, the number of jobs is a continuous value, and so very well should be a regression model. However, we'll go into further detail, but we did find a little bit of success using the decision tree classifier as well. And particularly looking at these maps were the average accuracy performed on, I believe, a 5 or 10-fold cross value score. And so for those who don't know, this is where we break the data into, we break the training data into, for a 5-fold score, 5 chunks of equal size. And that way, each chunk gets an opportunity to be part of the training data and part of the testing data. And so by doing so, it allows us to check for variance in the data. It also helps us prevent overfitting the data. But looking at the two models that we have, if we look at the left model and the tail end of it where it begins to converge, we see that it converges only around a 60 to 70% accuracy on that average CV score. Whereas if we look at the right side, it's converging much closer to a 90% accuracy. And so just off the bat, without tuning any hyperparameters and just looking to see, okay, what's the best, what's giving us the best start from the beginning, the decision tree classifier performed a lot better than the regressor, which was, again, rather strange given the variable that we're trying to predict on. Given that, we decided to take the decision tree classifier further and see if we can tune the hyperparameters there. So with that, we took the library, or we took from the sklearn library the module GridCV, and that allows us to grid search given a set of hyperparameters that we were looking to tweak. So the parameters that we were tweaking here were max depth and max leaf nodes. And we said, given this range of max leaf nodes and given this range of max depth, try to find the best model you can. And I believe we gave it a 10-fold CV validation. Actually, yeah, one quick easy way to check that is you can look to see how many split scores you had, and we had 0 to 9. So we had a 10-fold cross validation. And then the graph that you were looking at is we took that information and we organized it saying, hey, give me the best score for the mean test score. So that's here at the very bottom where it's highlighted. And then within those scores, since these are all the same, we ask for it to organize by the smallest standard deviation. So looking at that criteria for what we define as best, we picked the Model 10 uh, to be our winning model. So Model 10 had the hyperparameter of we set our max depth of an 18 and we had a max leaf node count of 216. So given those hyperparameters, we saw an accuracy of 97% on unseen data, which is phenomenal. So we have like a model that really captures what the Bureau of Labor Statistics is predicting moving forward. And with that accuracy, the max depth ended up becoming 91 with a total number of leaves, or max depth of 15 with a total number of leaves of 91. So yeah, so as far as achieving the goal that we sought out for in the very beginning, this is very successful. This shows the techniques that we were hoping to show, and it accurately grabs the or captures the story that we were looking to capture. As far as moving further, it would be interesting to go back and look to see how the regressor did better on the variable, or how the classifier did better on a continuous variable than did the regressor. I wasn't able to find anything that would inherently indicate why that took place, but that would be, I think, at this point, a meaningful future step. So thank you very much for sticking around for the presentation. I hope you learned something. Have a great day.